Welcome.
Thank you.
Thank you. Dr. Ahmed is the Cockrell Family Regents Chair in Engineering. He is the chairman of the Electrical and Computer Engineering Department at University of Texas in Austin. And I don't know how to start. I don't want to take too much time, but I want to say a few things. Ahmed graduated from University of Cairo, his bachelor degree in 1982, which happened to be the same university I also did my bachelor degree, but 15 years later than him. So there's 15 years difference, you can add or subtract, it doesn't matter. And you also then get 3 degrees at MIT, and his PhD was in 1987, which I noticed was 3 or 2 years after his master's. I don't know how he did it. But anyways, that is really wonderful. And he was with the university in Minnesota until 2010, before he was recruited to be the head of electrical engineering in Texas. He also has done a lot of work for industry as an advisor, and then he also started a company which dealt with watermarking and music and entertainment for 5 years, and the company is still going, although he left it. Then at that time, in the late 1987 and 2001, he took a partial leave from the University of Minnesota to co-found this company. And when he returned, they made a special institute for him where they were working on finding out what industry needs and then find solutions from within the university to solve the industry problems. He is very active in our society, which is the IEEE Signal Processing Society, which I'm very proud to be the president-elect. And Ahmed was a distinguished lecture speaker. He was on the board of governors. He was vice president, technical directions of this society. He is, of course, an IEEE fellow, and he also got the IEEE Third Millennium Award in the year 2000. Ahmed has worked really on a large, what distinguishes him, he has worked on such diverse areas, theory and also industry, and he is very successful in both. He is a pioneer in wavelets. This is when he started, before he started this company. And wavelets now is, everybody is working, many people have been working on that. And when he started at MIT, he worked on optical communications and on radar. And then he worked also on sonar for looking for Russian submarines and for oil explorations. He also worked with a company, I don't know if you remember, not the young people, but when President Reagan had the Star Wars mission and how to, kill other missiles by missiles. I can't remember it, but he also worked on that. And it's really, Ahmed also has given so many lectures, distinguished lectures, and the last time all over the world. Actually, the last time I heard you speak was you were a keynote speaker in Beirut, Lebanon.
Yes.
This was 3 years ago. So it's really a pleasure, Ahmed, to have you here, and thank you for agreeing to come. I know you are very highly sought after speaker, and also you have a lot of work, research, and administration. So on behalf of the department, we are really very happy to have you.
Thank you, Rabab, for this nice introduction.
And it's a great honor for me to be here, and thank you, Jane, for arranging the visit. So today I decided to talk about a topic that's a little bit different from what we normally get exposed to in electrical engineering or computer science. And I'm going to focus in particular on a project that we've been having with British Petroleum for a little over 3 years now. And the goal of this whole project was how can we actually use technology to augment our cognitive abilities. And in particular, how can we use technology such that technology works hand in hand with the human being so that we make the right decisions at the right time. And I'll tell you a little bit more about this in the next few slides. So I'm going to start with an introduction, and I actually borrowed slides from the presentation I've been giving to BP executives to set up the problem. And then I'll focus on this notion of man-machine symbiosis. And then I'm going to take a step back in a sense and provide you with sort of an overview of one of the current theories, maybe one of the more popular theories about cognitive biases and the cognitive biases that we all suffer from. I'll give you a few examples. This will put us in the right settings. And then I will conclude by telling you a little bit about some of the work that we're doing, the results that we're having, etc. Jane told me specifically that the audience is going to come from a number of disciplines. So I have a couple of slides that have, I don't know, some equations. We're going to go very quickly over these slides just to give you a hint of how things are working. Okay? And then I'll conclude by talking a little bit about the challenges ahead. Okay, so what's the problem that we were involved in? So around 2013 or so, 2013, 2014, BP came to us with a challenge, a particular challenge they had. They were still recovering from the Macondo event, and I'll talk some more about the Macondo event later in the talk. So one of their main concerns is to show to everyone that they're very serious about safety. And they, because of all of the studies that have been done around the Macondo event and the fact that to a very large extent it was driven by a series of bad decisions made by individuals and groups of individuals, all of which could have been averted, their concern was what can we put in place in order to make sure that that does not repeat again. But the other challenge that they had at the time was that the price of oil was very high. They were expanding their drilling in the Gulf of Mexico in particular. This was the time where, when I moved to Texas, oil was, Texas oil was always big in Texas. But the revolution, the shale, the fracking revolution, the effect of it was beginning to show up. But they had recognized it, and by 2013, the revenue, and in particular the margins they had on oil that they were putting out of the Gulf of Mexico was higher than the margins they were getting out of oil that they were putting from the continental shelf. But the problem was there was so much demand that they did not enough, and the workforce was rare. They did not have enough people who are trained to do the job. And as a result, people were being promoted very quickly to positions without having the experience that, say, 5 years ago or 10 years ago people may have had at that point. And one of the concerns was to make sure that these people, if they are exposed to situations, some of which may not be familiar situations, will still perform in a standard manner. Okay, so there is a standard way that the company, that the industry, that the federal government expects you to behave when you are presented with certain decisions or certain situations. And you have to remember, and I'll show you in a few slides, that these situations are complex, meaning that the people aren't dealing with one particular problem. They are dealing with multiple tasks simultaneously. And yet, you'd like them to perform in a standard manner. And this is both for safety reasons, but also for productivity reasons, meaning that if a particular task, a good trained crew would complete that task in half an hour, you'd like more or less all the crews to complete it in half an hour, let's say, plus or minus 5 minutes. You don't want a particular crew to complete it in 2 hours. But at the same time, you don't want a crew to complete it in half an hour, and then the next crew that comes in then has to spend the day fixing the problems that occurred during that half hour. Okay? So these were the challenges that we were dealing with. And the approach that we took is, yes, we're going to provide technology that will augment the abilities of the decision makers, workers on the rig floor, upper decision makers in management. But the technology isn't meant to be a replacement for a lot of the processes that are currently in place. So having this technology doesn't mean that you throw away all of the processes, the rules, the regulations, the procedures that the company has to put in place. It doesn't mean that training is not something that you would stop worrying about. Okay, so we're not going to completely replace them. And technology is not going to displace you completely. So we continue to do what we're doing, except that we're augmenting this with the technology and hopefully to get better performance. And the particular tack that we took was that the way we're going to try to solve this problem, and this is a partial solution to the problem, was that we were going to focus on how information is presented to the human being. So the question was, what do we show? How do we show it? When do we show it? And information here is not just data that a human being might see on a screen. Information may be the connections that we have. So it may be that at a particular point in time, it may be best for me to connect with Rabab. She might tell me some information, or she might ask a question, or a joke that might get me to maybe think more clear. Yes, it's always good to connect with you. Okay. Other times I may have to connect with Vikram because he's going to show me a nice mathematical equation, and that will be the intuition that I see. Okay, so that's the key here. And just to put this in context, I like to use this example, and this example is really taken from an introduction to a chess book written by Kasparov. And he was describing in this introduction a competition, an online competition, chess competition. And it was a unique competition. So normally when you go through these online type of competitions, or when we offer our courses online, we would like to know that if Jane is taking the exam, that it's Jane and it's not Vikram taking the exam instead of Jane, or there are not multiple people working with her. In this particular case, there were no such constraints. So you could be yourself, you could be a team, and more importantly, you could be a combination of man and machine. You could have computers working with people, or you could have computers. And what they found in this competition, some of the results that out of the competition were not too surprising by the time it happened. So the best machine out there was able to beat the best human chess player, which wasn't new because it had happened before. But what was interesting, so machine can be better than man alone, okay, in this particular context. But what was interesting is that the team that won the competition was not a team made of the best chess players. And it was not the team that had the best equipment, as in the computer that had the most flops and the most memory, etc. It was the team in which the machine, the computer, was best tuned to the human beings, meaning that the way that the human beings interacted with the computer, the way that the human beings could feed back their intuition into the computer, and how the information was presented back to them from the computer, was the best amongst all of the teams. And so the lesson from this was that in certain contexts, okay, so this is not universal. Some of the tasks we do are mundane, and we're not going to be as good at these tasks as a machine that's doing it on our behalf. But as we continue to advance and replace these mundane tasks by automation, there will always be tasks in which, when we work with a machine, if the machine and the man are tuned to each other, if this process is designed correctly, at least this is the hypothesis, then we're going to do better than machine alone or man alone. Okay, so it's not a question that if we do great, at one point the machines or the computers will replace us, because there will be always tasks in which if we work in tandem with the computer, we're going to do better than computer alone or man alone. So that was the whole thesis of this work. And let me now take a step back and talk a little bit about the cognitive biases, which will give us an idea about the specific problem that we're trying to solve. Okay, so this idea of cognitive biases is something that people have worried a lot about. And in particular, there are fields in economics, behavioral economics, and people worry about the fact that we, as human beings, are not really rational decision makers. We think we are rational decision makers. We're not, okay? And there is this theory, which is the most prevalent theory that explains this irrationality in our behavior, that says that conceptually there are two systems at play whenever we make decisions. So there is one which is referred to in the literature as system one. It's really not one system. It's a multitude of systems. But this system is the way our brain is connected. And it captures information that we may have learned intuitively as we're growing up. But it's also information that we have collected as a species over evolution, and perhaps other species that contributed to ours. So for example, when I touch something hot, I take back my hand. I don't analyze, this is that temperature, and this is what's going to happen to me, and then I make a decision to retrieve it. These kinds of systems, these types of processes exist in us as humans, but they also exist in animals. Okay, so a lot of the behavior that animals have are because of systems like that. I mean, this kind of behavior. The second system is the system, or the second process we use for decision making, is the process that we all think as humans, we're superior because we use it all the time. We don't. So this other system is where we take information, we analyze it, we dissect it, and then we make decisions, and it's very rational, but it's very slow, and it consumes a lot of energy. Okay? So the reason that we were successful as a species, and the reason that in our everyday life we succeed and we survive, is because almost all of the time we use the first system. We take information, we discard 95, 99% of that information, we look at patterns between what we've seen and what's registered in our brain, and we make a decision very quickly. Doesn't cost us much energy, and it's very quick. Every now and then, we use this system, and when we use this system, we make the wrong decisions because we discarded information that we should not have discarded, and then we arrive at wrong decisions, okay? And we all have experienced this. So you go to a shoe store and you buy some shoes, and then you go back home and you say, why did I buy this pair of shoes? Okay? Sometimes it's more dangerous. So you make a decision, like the Macondo decisions, which can lead to a matter of life and death. Sometimes it's not a matter of life and death, but it can have serious consequences. So you marry a person, and then you discover that maybe I should not have married that person, right? So these are serious problems. I mean, they go from the mundane to the more serious, but the consequences are important. And I'll just give you a couple of examples. I'll show you those examples very quickly. They're very trivial if you think about them, but if you look at these problems and you try, most of you, I mean, if we do these experiments, and you try to answer the questions that I'm going to show you in a second, the probability that you make a mistake is high, even though there are trivial problems, okay? So one problem that people use to illustrate this is they ask you this question, a bat and a ball costs $1.10. The bat costs $1 more than the ball. How much does the ball cost? You can, I don't want answers, but you can think about it. And what happens, and in particular, if you force system one to kick in, so if I get you to multitask, because we're not good at multitasking, okay, most of the people will say one is $1 and one is 10 cents, which is not the right answer because you all know how to do algebra. But again, if I force you to make a decision, even if you're trained, most of the people will make a mistake, no matter how trained they are. The other example is an interesting one, since you're teaching a probability class. And this is this one. And I actually ran this one by one of my colleagues who also teaches our probability class and is really great in probability theory. So, there is a woman, and she's called Linda. She's single, she's outspoken, she's very bright. When she was a student, she was deeply concerned about discrimination and social justice. And then people are asked, which is more probable? Is she a bank teller? Or is she a bank teller and is active in the feminist movement? Okay? So think about it. And I would be ready to bet that a majority of you would have said that she is a bank teller and is active in the feminist movement. But anyone who's been taking Vikram's probability class would know that if I put more constraints, then the event becomes less likely, because this event is included in event 1, so event 1 is more likely. And again, you can ask this question to somebody who is a statistician, who knows probability theory, and they'll make the mistake, okay? So the point is, even if I tell you that I'm going to put you in a context in which you're likely to make these mistakes, but if I put the right pressures on your time, multitasking, etc., you're going to make these mistakes. It happens to all of us, and it happens all the time, okay? So what we're trying to do is we're trying to avert these mistakes. We're trying to avoid these mistakes by making sure that we trigger the right mechanisms in your brain and the right interpretation of the information. There is another example, and this example is a fairly interesting one, which comes into play a lot in the context in which one is reading information and needs to make decisions about this information, including in the Macondo event, including pilots, including, doctors and the like. So if I ask you to add the digits in your phone number, if you end up with a large number, I mean, these are real experiments that have been performed. If you end up with a large number, and then I ask you, how much are you willing to pay for my iPhone, you're going to give me a large number. If you end up with a small number, on average, you're going to give me a smaller number. And this carries over in many, many contexts. So the students or the professors, before you go to your department chair, if you are interviewing for a position and you're asked how much you expect as a salary, if you start by giving a high number, okay, not an unrealistic number, okay, because then people will dismiss the information. But if you give a high number, on average, you're going to get a higher salary than if you give a low number. In lawsuits, the lawyers that ask for larger damages, on average, will end up with larger sums than those who ask with smaller damages, okay? And people know this. So for example, if I'm calling you about a donation, if I tell you it can be 100 or 50 or 30, on average, I'm going to collect more money than if I tell you it can be 20, 30, or other, okay? Because the other wants to get you to do more. So this is an important problem, and the first example I gave you in particular is very interesting because there is no relationship between the digits in my phone number and the price of a bottle of wine or the car that I'm trying to sell you, right? So the point is that in the context of work, I may be reading information that is numerical, and because of the prior conversation I've been having with someone else, or another task that I was dealing with, then my brain might latch my anchor on information on a number, and then that number is what I'm referring to internally as I process other data coming to me. And of course, that can be catastrophic, okay? So this is something that we need to be dealing with. Another issue that's interesting, and it turns out that has been debated for a long time, is when I present you with information, how do you take that information? Okay, so there were 2 points of view that had been expressed philosophically a long time ago. One point of view is Descartes' point of view, who probably is the way we all think we behave, who said that if I present you with information, you're going to analyze the information, and then you're going to decide whether to accept it or not. Okay, so if I make a claim or I tell you a story, if I'm a politician or whatever in the news, I give you a story, then you're going to analyze the story, and then you're going to decide whether it's true or not. Okay. The other point of view was, no, if I present you with information, then you're going to absorb this information and you're going to assume that it's correct. And then if it proves to be incorrect, then you throw it away. And it turns out from the various experiments that have been performed that this second point of view is actually the correct point of view. Meaning, if I present you with information, then you're going to presume that it's correct. Not only that, you're going to try to retrieve information from your memory that confirms this information. And if you're unable to do so, or if you're presented with a lot of contradicting information, then after a while you're discarded, okay? So this is why if I go in the supermarket and I'm buying something, and if I see a message, which I'm seeing in very quickly as I'm paying, that message has a lot of effect on me. So I might actually end up buying something or other. Or if I'm watching a movie where actually a lot of my senses, or a lot of my analysis is also dumbed down, then whatever I'm going to see in the movie is going to register and stay with me, be it something, be it a political statement, or being a nice watch that the actor is wearing, or a nice car that the actor is driving, etc. Okay? So, and again, there were a number of experiments performed on this, and one of the most important ones is there are computer games in which we can test this hypothesis. So you put people in front of a computer, you show them information, you color code the information. So if it's in green, it means it's right, and if it's red, it's incorrect. And the people are supposed to be judges and pass sentences on somebody who may have been accused of a crime. So the person might really be innocent, and you show them information that is incriminating, but you show them in red. So you're telling them that the information you're telling them is incorrect. But you keep showing them incorrect information and a little bit of correct information. On average, they are going to sentence the person to give the person a long sentence. Now, fortunately, it's a game, but it gives you a sense of how things are done, okay? How our brain processes the information. We tend to believe, and then it will take us time to disbelieve. And again, as a species, this is good, because I would like to benefit from your experience as opposed to me every time relearning what you've gone through. Okay, from our concern, we want to model these phenomena. And so we also need to understand how susceptible we are to all of these phenomena. So there are various experiments that have been performed which give you some sense about under which circumstances you're more susceptible to suffer from one of these phenomena than in others, and how long these phenomena might last, so whether they're going to last for a few hours, for a few weeks, etc. And all of these are experiments that are qualitative experiments, which at some point we need to take and then convert into quantitative information that we can act upon. Okay, so let me just show you as an example of how this works, talk a little bit about the Macondo event. Okay, so the Macondo event happened a few years ago, and what had happened is that BP had discovered oil at a particular location, this Macondo location. When you drill for oil, you have super big rigs, very expensive, with very sophisticated equipment, large crews. When you discover the oil, then at that point, what you do is you want to remove this expensive rig and replace it by a smaller, less expensive production rig, because you're done with finding the oil, with putting the well in place, and all of the instrumentation. But the problem is, you have dug a well, and you have gone into the production zone, and oil or oil and gas may be coming up. So what you need to do before you leave the location, before you can move your well, and so this is our well here, and this is the rig, and this is the well. So before I leave the well, the rig, what I need to do is I need to take my well, and I need to cover it with a cement cover at the bottom floor, and then put another cover, underneath the bottom floor, the sea floor, and then put another cover up there. And this cement cover better be strong enough to sustain the pressure from the oil and gas that wants to go up, okay? Because otherwise I move, and then I'll have a gush of oil, and it'll be a problem. So what happened is when they did the discovery, this was happening, and the crew wanted to go home, and there is a certain processes that they need to go through before they can cap and know that the cap is well in place, and then they can move away. There are a number of errors that have happened. I'm not going to touch on all of them. I'll just illustrate a few. So for example, one of the issues they had is that the cement job was done in a non-standard way. Okay, so I'm not going to talk about that, but that had implications. And the way that the decision was made about the cement job and what cement to use was problematic. And it also had an influence on, or should have had an influence on the events that happened later. Okay, so when I talk about the cognitive biases may impact a particular decision, which also may then have impact on decisions made by other people at other times. And so it's important not only to capture these biases and the way the decision was made at a particular time, but it's also important to somehow relay it to people who are going to make decisions downstream from that particular point. So what I'm going to do is I'm going to illustrate a couple of issues that had to do with the blow-up. Before they, one of the tests that they have to do is they have to test that the cement job is going to be solid enough. And the way they do this is during the oil drilling, the main drilling pipe is full of mud. Okay? The mud is there because as you drill, there is a lot of heat that is generated. There are particles and rocks that are broken. And the mud allows you to take that heat up, and then it also allows you to take the debris and take it up. Okay? One of the things you worry about during the drilling is that as you drill, you break certain, you make fractures in the rock, or you make fractures in the actual well. And as a result, you can have either a leak out of the well or a leak into the well. And the most problematic, the one that was problematic in this case, was a leak into the well, because if you have a leak into the well, then what happens is that leak will start to push the mud up the well. And as it pushes up, the gases start to expand, and so their velocity continues to increase. And by the time they reach the surface, it's like having a huge weight come and hit the rig. And furthermore, it's explosive. So if anything happens, it explodes, which is exactly what happened here. Okay, so what they do is they have a valve that they can close, and they can try to do a test on the cement job. Before they do the test, they try to remove the mud because in this particular case, they didn't have to do it, but this was their plan. They were planning on removing the mud from the well and replacing it by seawater. Seawater is much lighter than the mud. Now, the mud, if the cement isn't strong enough, the mud plus the cement might be strong enough to sustain the pressure from the oil and gas. But seawater plus cement may not be enough. The test said what you do is you replace some of the cement by seawater. There is a particular liquid that you put to separate the seawater from the mud. It's called the spacer. So there were other issues with the spacer because BP wanted to get rid of certain material that they had on board. And so instead of using the normal spacer, they used these materials to create the spacer. Because if they created the spacer out of this material, then the regulations, right or wrong, allow them to dump that back into the ocean as opposed to have to take it back to the shore. So this was good for them. Okay? And then once you replace the mud by the seawater and you close the upper valve, then you measure the pressure in the well. So you're supposed to open the well from up to atmospheric pressure, and you measure the pressure. The pressure is supposed to drop to 0 psi and stay at 0 psi. These guys did this test. It's called the negative pressure test. What happened is the pressure dropped to 0 psi, and then it went up again. Okay? So that would indicate a problem, because the only way it would go up again is if there was a leak, and then there was pressure coming from the gases entering into the pipe, and that was increasing the pressure up. So they repeated the test. And again, same thing happens. It dropped, and then it went up again. Now, they got together as a group, and they explained it away. So somebody came up with a theory why the pressure came up again. Okay, I don't remember the terminology, but they came up with a scientific explanation why that would happen. Now, the person in charge of the oil rig was not very convinced and said, we have to repeat the test again, and this time we're going to do it into the kill line also. So the kill line is one of those lines on the side which you use to also put material down to the seabed. So when they did it again, the pressure in the kill line dropped to 0 and stayed at 0. But at the same time, the pressure in the main line did not stay at 0. It went up again. Okay? So that should have raised a red flag. But instead they said, well, in the kill line, the pressure was at 0, so we're fine, and we're going to move on. Okay? So here, what happened is you had a number of experienced people. They knew what was going on. They had other incentives. Okay, I mean, this was playing in the back of their mind. They wanted to get done, they wanted to go home, etc. From a company standpoint, they want to finish this job because it's costing them money. And somehow all of these people, because of the pressures they were under, looked at the test and concluded the wrong thing, even though they were all together. And they latched on an explanation provided from one particular person. Okay? Okay, so once they'd made this mistake, and I think I'll just focus on this, then their next job, since they decided that the cement was strong enough, their next job now was to pull the mud out of this riser, so this column that goes up to the rig, and then replace it by seawater. Okay, so the way they do it is they have a pump, and the pump brings this mud up to the surface. And when it's done, and when the spacer comes out, then they keep replacing it by seawater, and they would be done. As this exercise was proceeding, they were pumping at a constant rate. And if you pump at a constant rate, then your pressure should not build up. But there is a point, you see this red curve here, that's jagged, and even though the pumping rate was constant, the pressure started to go up. Okay? And again, this should have been a telltale sign that something is wrong. And what's important to recognize is that there are multiple people looking at this information. Now, they're doing all multiple tasks, but there are multiple people looking at this information. One of them is called the driller. It's the person on the main floor who controls the actual drilling, and he controls at the same time a team of other workers. Another is the mud loggers, which is another team at a different location on the rig, who's just looking at this information. And then it's the company man in his shack, which is really, in this case, the BP person who's in charge of the entire rig. Okay? So there are multiple people looking at the information, and somehow this escaped them. A few minutes later, the mud was completely out, and then the spacer fluid arrived at the surface. Okay? So at that point, they're supposed to do an analysis of the spacer fluid before proceeding. To do an analysis of the spacer fluid and before proceeding to dumping it out the board, what they had to do is they had to stop the pump. So they stopped the pump completely, and then while the pump was stopped, the pressure started rising again, okay? Which is a big anomaly. I mean, this immediately tells you that there is a leak in, there's something that's increasing your pressure because you're not pumping at all. And again, that escaped them completely. After a few minutes, then they restarted the pump, and as they were doing this, they finally noticed that the pressure is going up. And it's only at that point that the driller realized that something wrong was happening. At that point, they literally had a few minutes to live, because after a few minutes, they were hit by the kick, and it exploded, and the driller and the other person next to him and others, many others died. Okay? So what we're trying to do here is to make sure that in a situation like this one, you are presented with the information in the right format at the right time. Okay? And again, there are multiple information that you are exposed to. Okay, so what's the approach that we attempted to take here? So the approach that we attempted to take here is philosophically similar, at least in my mind, to the approach that as a profession we took back in the late 70s and 80s, or we continue to do today, when we're approaching audio, image, and video coding. What happened in particular in the 70s and 80s is that we took a lot of information from other literature, not the technical literature, so the psychoacoustic literature, for example, and these were experiments that weren't designed to check on whether, how accurately we should represent a piece of audio. It was designed to understand the kind of pathologies that we as humans may suffer from as far as seeing or hearing. Okay? We took that information and we converted it into mathematical models that allowed us to predict whether a change in an audio signal or a change in an image or a change in the picture is going to be perceptible by a human being or not. These models were not models of our actual perception, meaning this is not an explanation of how biologically we see or how we perceive a signal. But they were giving us accurate information about whether a particular sound was going to be perceptible in the presence of another sound or not, or if I change it a little bit, or whether the phase is important or not. Okay? And obviously this was very successful. and you all knew this because some of you are working on video compression here, but you all use your MPEG video coders, your AAC audio. I mean, you're using it all the time on all over your devices. So the idea is very similar. We're going to take qualitative information that comes to us from psychologists. We're going to try to convert it into mathematical models that are actionable. These mathematical models do not necessarily explain where the cognitive biases are or came from. Okay? I'm not trying to explain how the brain is wired. But there should be precise enough to enable us to predict how a human being is going to behave in a certain situation, and precise enough that if we show the human information the way that we're supposed to show it optimally, that will have an effect on the decision of that human being. Okay, so the way we're doing it is we're on the oil rig. We get access to the raw data coming from all of the sensors on that rig. Okay? So all of the sensing information comes to sort of a centralized location in which we're going to do some analysis and some processing and decide on how to show the information. Now, this information also goes into automated algorithmic approaches that are task-specific that BP and others were developing. So, for example, if you are making what they call connections, which is you're putting sections together and then you're pushing it down the well, well, there are certain tests that we can get from the measurements on pressure, rate of penetration, friction, etc., that might tell us whether the fluid is circulating properly or there's a problem, etc. And so there are algorithms, so there are machine learning algorithms that are also taking the information and making certain decisions. And the way we think about these algorithms is that they are presenting us with yet additional information, except that that information has been processed in a particular way. Now, key here is that the driller who is on this drill floor, on this rig floor, doesn't know the assumptions that went into the design of these machine learning algorithms. Okay? The same way that a pilot flying a plane doesn't know how the algorithms that are driving the autopilot were designed. Okay? They don't know the limitations. They don't know, how it was structured. However, this is additional data that's coming to us. Then in addition to that, we have behavioral information, meaning that we are tracking the person. We're tracking the information that's presented to the person. We're tracking how alert they may be. We're tracking how long they've been working on the rig floor. And in the more complex context that we haven't dealt with yet, where you're also talking about groups of people, you're also tracking the communication and what was been happening. So what someone told me as opposed to just messages. So what I've heard and the kind of interactions that are happening to the group. And then you make certain decisions on exactly how to interact with this person. What to present to the person, how to present to the person, and what kind of other interactions you may force between different people on the team. Just to give you an understanding of the context in which we're dealing, the driller sits on a chair like this one, and they typically have a couple of screens in front of them. These screens provide them with direct information about what's happening at this particular point in time for the task they're doing. So the weight on the drill, how fast it's drilling, where you are down the well, etc. On the right-hand side, at least on the rig that I went on, there is another dashboard that has all sorts of information. Now that dashboard is some distance away, okay? And it has a ton of information. So the person is supposed to be looking at that dashboard and seeing more information than what's only presented on these two screens, and supposedly understand whether there's a problem, there's no problem, I'm doing fine, etc. Okay? The reality is, because of the work that they're doing, they at best will be looking at this screen once every, 10 seconds, 1 minute, whatever. On top of this, these drillers, so this is the driller, these guys control also a team of other human beings who are doing various other tasks on the rig floor. So for example, they may be asking others to connect these tubes together, or they may be asking somebody to take a sample from the mud that's returned, okay? So it is a very complex task in which a person is dealing with lots and lots of information. And part of what we were trying to do is guess on how to present information to this driller. And the solution we elected was to use something like the Google Glasses to overlay information on top of whatever they were doing or whatever they're seeing. Okay? So we may show them the information, and the information that different people might say, even if it's the same information, may be presented in different ways. So I have another colleague that was working on this issue of your preferences in terms of how to present the information. For example, something that has nothing to do with this, I may like to say a bar graph, and somebody may like to see a pie chart. Okay, so we get it. I get it best with a bar graph. Somebody else may get it best with a pie chart. Okay, that's the kind of things that we're also talking about. Okay, so I'll just skip this slide and take you in the last 15 minutes into one of the problems or a subclass of problems we've been looking at. Okay, so so all of the discussion from now on is going to be focused on a hypothesis, a binary hypothesis testing problem. Okay, so for those of you who haven't had detection and estimation theory, basically these are problems in which I'm asking a yes or no question. So I show you information, and I say yes or no. Okay, so do I have a flu or I have no flu? Okay, is somebody called me about the fire. Is it a fire or is it a hoax? Okay, so I need to make this determination. In this context, a lot of the decisions that I need to be making come under that flavor of problems. So at a very, very basic level, any worker on the rig has the right, regardless of where they are, whether they're the top executives or the lowest person on the totem pole, they have the right to stop work. So if you feel, because it's so dangerous, so if you feel that something is not right, you have the right to stop the work across the rig. Okay? Now, obviously, they don't like you to do this every 5 minutes because it's very costly, but you have the right to do this. Okay? And just to give you an example, where you don't stop it. So when we went on the oil rig, we took a lot of training before we went there, but when we went on the oil rig and you are in your room, the bathroom where you take your shower, if you keep the door open longer as you're exiting than what you should, the steam can trigger the fire alarm. And it happens. And if it triggers the fire alarm, everybody evacuates. Okay? And so that costs them thousands and thousands of dollars because it takes about 30 minutes for them to clear a trivial fire alarm like that. Okay? So in the particular example I'm showing you here, is one in which every 15 feet, as they dig 15 feet, they stop digging, and then they remove the bit, and they do a flow circulation. And what they're trying to test is whether there is a leak that happened as they were going through this process. So they break a formation, and there's something fell in, and so we have either a leak out of the well or into the well. How do we measure this? Well, you measure this because if there was no leak in the well, then the amount of fluid that you're pushing into the well should be equal to the amount of fluid that is coming out of the well. So the volume should be the same, and you also look at the velocity in which things are coming in and out, because that tells you if there is a leak. If there's a leak in, then as the gas expands, then the flow velocity also goes up. Okay, so the way they do it is they stop and they look at the fluid coming back in, and they measure the fluid that they pumped out, and they look into a container, and at some point in time, the fluid should stabilize in the container and should be equal to the level that you put into the well. Okay. The way that you do this test is before they start the test, based on what happened 15 feet before that or 15 before that, they come up with some lines, and as long as the measurements stay within these lines, they say it's okay. And if they depart from these lines, then they say it's not okay. Okay? So usually, in order to do these tests in an environment that is not very deep, you take about 30 or 40 minutes. If you're going to go into the environments where they were planning to dig in 2018, which these are the environments in which you're talking about 20,000 feet or more under sea level, then it can take you an hour more. Okay? During that hour, you're not digging. Okay? You're just waiting to see what happens. And not digging means that it's a great expense to you. So the problem that we're trying to deal with is, can we make this decision with the same accuracy? I mean, there is a business decision that needs to be made at that point, which is your tolerance for error. Okay, because I mean, I'm not, even a human being makes a decision about is there a flow in or not, it's not like there is zero barrel going in or out. So you have to make a decision. I'm willing to live with, let's say, a barrel or two going, an error of a barrel or two. Okay, but the point is, we would like to speed up this decision. Well, anybody who's taken a course a slightly more advanced course in detection estimation theory knows about sequential decision making. Okay, so in sequential decision making, what you do is, it's not a yes or no decision. What's going to happen is, I would like to make a decision with a given accuracy. I would like to be able to tell you that with a probability of 99.999, the decision I'm making is an accurate one. Okay, so we decide on that number. This is a business decision, okay, because there are consequences, there are dollar consequences associated with that. If I make the decision earlier, it saves me money, but if I have an error, it's going to cost me potentially a lot of money. Okay, so let's suppose that this has been solved. So algorithmically, if I'm using a machine to solve this problem, I know that this theory of sequential decision making will, on average, give me faster decisions. And so what happens is, I get data. If I have data enough to make a decision reliably, I'll make a decision. If not, then I'll take more data. I'll keep doing this until I have enough data to make the decision reliably. And the point that we're trying to make, so this is what's illustrated in this curve. Instead of looking at all of this, I would like to see some of the data and then make a decision. With a human being, we would like to see if the human plus the machine, in some sense, there is a way of even making things better. Okay, so we studied this problem, and don't worry about these equations. I just want to use them to illustrate a particular point. So for those of you who have had detection estimation theory, and one of the simplest problems, I have Gaussian data, and it's independent, and let's say, and I'm looking, so all of these binary hypothesis testing problems, you give me lots of data. If it's binary, I'm going to reduce it. There is a mathematical way, depending on the statistical setup. I can reduce it to a single scalar, which you can think of as sort of your belief or your confidence, and in the way that a layman might think about it. And as this number, if my belief exceeds a certain threshold, then I'll say yes, and if not, then I'll say no. Okay, so that's more or less the way you can think about it. If it's a machine that's thinking about the data, then the order in which you present the information to the machine, as long as you present to it all of the information, is not going to matter, because in the end, it's going to make the same decision. For a human being, that is not true. The order in which you're going to show the information to the human being is going to matter in the decision of that human being. And so if you take the mathematical expression, I mean, the point is the small li's here is sort of what happens is I get new data for a machine. For a human being, there is the models that people have developed in behavioral economics and which we've adopted here are ones in which either the way the new information is absorbed is modified, and or the thresholds that are being used to make decisions are modified. Okay? And I'll give you examples of that in the next few slides and talk a little bit about the implications. So there are various biases that people talk about. One of them is the confirmation bias. Okay? So another one is the anchoring bias that I talked about, and a third one is this primacy effect. Okay? So the primacy effect is I see some information, I latch onto that, and anything that I see after that, I don't give enough weight to, or I don't give much weight to it. Okay? The confirmation bias is the one where I'm told something, and which is what we all do, I'm going to believe that information. If you present me with additional information that confirms this, then I'm going to give this information a lot of weight. And if you give me information that contradicts that, I'm going to give it less weight. Of course, after a while, if you give me enough information that contradicts it, I may change my mind. But it might take me longer for this to happen. Okay? So the point is, you can play with these weights, which are data dependent. Okay? So they depend on the data that you've seen up to this point, and they depend on the data that you're seeing at this point to capture the kind of biases that we all experience. There are other models which I'm not showing here that also capture the changes that might happen in the biases, in the thresholds that you might be using for your decision. Okay, so we've looked at two classes of problems. We've looked at a class of problem in which I'm going to show you all of the information, and you're going to make a decision at the end. We're going to use a sequential process. So I'm going to show you information, and you're going to show this. Using this information, you or the machine are going to make a decision at a certain point. And there are two curves on the left-hand side and two curves on the right-hand side. So on the left-hand side, the dotted line, the dotted red line, is what you get if you use a sequential test with the right theory. So this is a very specific case because the easiest way of dealing with the sequential test is if I have independent, identically distributed data, and you give me the performances that you want to reach. I can compute the thresholds. I can also compute the average number of observations that you're going to take, and I can run the experiments, and that's what happens. The blue curve is one that represents how a human might deal with this information. And it represents, on average, the case where the data is presented in a random way. It takes into account the changes in the thresholds that the human being might undergo as they see data. On the right-hand side is the dotted line. The red dotted line should be the same as the one on the left-hand side, your left-hand side. But the blue line is one in which there is an agent that decides on the particular order in which the information is going to be presented to the human being. And if you do so for a given performance, I don't know exactly what thresholds the person is going to use. But I can guarantee you that for any performance level, which results from whatever is happening in the brain of that person, the average number of samples that the person will take to make a decision will be less than what the sequential test is doing. Now, the other problem, and I'll skip about the math, is a more interesting one, and is a very relevant one, which is I'm going to play a different game now. Instead of having all of the data and then sequentially showing you the data and then you decide when to make a decision or not make a decision, I'm going to beforehand decide to show you a certain fraction of the data. Okay? So I'm going to decide to show you 5% of the data or 10% of the data. And I'm going to decide on what order to show it to you. And what I'd like to do is I'd like to end up with a performance similar to that of the best human being, say, that has access to the entire data. Okay? And the point that we're trying to solve here, there are two things. One is what is this optimal ordering, and can I compute it in real time? Okay? So the curves that I have here, and maybe I'll go to the next slide instead of this one. Okay? And then they make decisions. And this is what we refer to as our receiver operating characteristic. Basically, it tells us what's the probability that you will make the right decision in one case. And so let's say there is a leak, and I say that there is a leak when there is a leak. And this other curve is the probability that I will say that there is a leak when there is no leak. Okay? So ideally, what I'd like to do is I have this probability of false alarm equal to 0. And my probability of detection equal to 1, which I really can't do. But generally speaking, I would like to have a very steep curve that goes up this way. Now, of course, if I say always there is no leak, then I will never have a probability of false alarm, but I also have no probability of detection. And if I always say that there is a leak, then I'll be up there where I will always detect a leak, but also all the time that there is no leak, I'll be saying a leak. Okay? But generally speaking, I would like to have something that starts at this 0 and then goes very quickly to 1. So you have this curve, and then underlying it, which you cannot quite see, is another curve which takes the data that you have and then uses an interesting variation on an algorithm that's well known in computer science, the subset selection problem, that enables you to compute in, and I can go back, so if I have n data points, wasn't p? Yeah, okay. So if I have n data points, it allows me to compute the right solution in order n squared. It should be log n prime, where n prime is the number of samples that I'm retaining, as opposed to having to go over all of the possible combinations of the data, which obviously is untractable. And you can do this, and it guarantees you to find the solution that is within a certain predetermined precision from the optimal solution that you would have obtained through this very complex process. Okay, so the point of all of these, okay, so these are, the same thing is true with different biases, which are the curves that I'm showing here. This is the confirmation bias. This is the curves with the anchoring bias, and this is the bias in which if you believe something, it's the confirmation. It's another version of the confirmation, but it's a temporary one. So if I believe something at a particular point in time, what I'm going to discard or not discard will depend on what I believe in. Okay, what I skipped in all of these curves is there is another variation, an ad hoc variation that also allows you to order the information. This ad hoc variation also has low complexity. But depending on the type of biases that you're dealing with, it may not give you the right solution. So sometimes it doesn't give you the right solution in this band or in the middle band or the end band. But typically what you're interested in is the low probability of false alarm and a high detection rate. Okay? Let me talk a little bit about this slide. One of the things that we did not address so far in the research, which is extremely important but extremely challenging, is that as I'm presenting you with information, you're not only analyzing this information, you're also recalling information that's stored in your mind. The information that's stored in your mind, your prior experience, is information that the algorithm or the machine or the computer does not know. It might know that this person, this driller, is on this rig and also was on a similar rig that was 60 miles away. So the formations might be similar. But they don't know exactly what, the algorithm or the machine does not know what's in the brain of that driller. As I'm presenting you with information, I would like you to retrieve the relevant information in this case. And sometimes what I need to show you for you to retrieve this information may have nothing to do with the information that's presented to you at this point in time. So again, I may be working on a problem, and because of my biases and other discussions, I may be going through the wrong direction. And let's say I get suddenly an email from Rabab, and it's a joke. But that joke gets me to think or gets me to remember something. And when I go back to my problem, suddenly I realize that something is wrong because I've retrieved information. Okay? So we need to have a way of modeling this so that the information that we're presented is not just modeled in terms of how these beliefs are changed and what kind of biases we're dealing with, but they also depend on information that the machine, the algorithm, is blind to, okay? Because the algorithm cannot read what's in your brain. And the algorithm then would also need to know that you actually have retrieved this information, which the only way it can know that you have retrieved this information is by asking you a question. You have to respond to some kind of question or some kind of challenge so that we know where you sit. Because otherwise, I cannot guess what's happening in your brain. Okay, so this is a problem for which we have no solution yet. And I'm not sure that anybody out there also has a solution. Okay, where we're going with all of this is the work that we do is it's mathematical training. Then there are simple experiments that are performed typically in the form of computer games with students in front of a terminal. And then ultimately, there is an oil rig simulator in the Department of Petroleum where you can actually test the algorithms and see if they work or not. And this particular person here, when the project started, this was the Dean of Engineering at the University of Texas. And as of June, he became the president of the university. He was the first president, the first engineering president of the university. Okay, so there are many, many challenges, and this is my last slide, that we need to be dealing with. One of them is context awareness. Okay, so I really need to know, in order for this to be very precise, I need to know whether you've had 8 hours of sleep, if you have a problem at home, what's happening around you, etc. Something that we haven't included yet. This information asymmetry is extremely critical. And this, I've alluded to this already, which is that as I am using a particular algorithm, autopilot, whatever automated algorithm is out there, I don't know how it was designed. I don't know the assumptions that went into it. I don't know what will make it break. Similarly, any system that is out there that's looking at me doesn't know what kind of experience I have, what kind of, what I've learned, etc. So it doesn't know what is going to be, what's in my memory and what I can recall. There is this issue, I'll just conclude with this point. Should I trust the system? Okay. So this problem is a critical one. Ultimately, we're trying to make man plus machine better than man alone or machine alone. But there is a risk. There are 2 risks involved. One risk is that you overtrust the system. And if you overtrust the system, then you're going to completely tune out. Okay? And if you tune out, then you defeat the system. Okay? The other thing is you do not trust the system at all, in which in case you turn it off. And we've seen this in a number of accidents. Okay? So for example, the Korean airline accident in San Francisco was precisely because somebody disconnected the autopilot, and then they were unable to land the right way, and they crashed the plane. The Air France accident was a case in which the autopilot disconnected. They did not know exactly what was going on, and they made the wrong decisions, and they crashed the plane. Okay? So I know I went over time, but let me just close by thanking my collaborators. And Sarah Murad are 2 of our students who have been deeply involved in this work, and actually the final results I showed are all of their work. Professor Sanjay Shakotai is one of my collaborators at the university. He's the one who works on how to display the information, as in graph chart versus pie chart and the like, and learning it by learning on what's happening using social network type of theories. Gustavo de Veciana is the one who worked on the connection problem. Reed Hasty is a psychologist who happens to be in the Booth School of Business at the University of Chicago, and he was providing us with a lot of information and advice on what's happening in the literature in psychology and what works and what doesn't. And then Mick Leary, Hendrik de Jong, and Freydun Abbasian are all. So Mick Leary and Freydun is the VP of engineering. Mick Leary was one of their top executives. And Hendrik worked for VP, and all of them, again, played a big role in educating us, providing us with information, providing us with access, and the like. So with that, I conclude, and I apologize for going 10 minutes or 7 minutes, but I think you take 5 minutes out of those. So.
Yes.
So any questions or before?
Ahmed, this morning you alluded that you're doing work because there is you're going to be interesting work, and it will be forming a big project where you will get funding from NSF.
So there is
related work.
Yeah. So there is a NSF is going through a pre-proposal phase for engineering research centers. Okay. So with some of our colleagues in Berkeley and Chicago, Northwestern, there are notions of extending this work, okay, to deal with from the more mundane problems, as in I bought the wrong shoes, or what do I do in a classroom setting so that the students understand or learn the information faster, to the more critical decisions, such as what we're dealing with here, or say a hedge fund. And when do I make a trade? So I'm not talking about the algorithmic trades. I'm talking the cases where there are human beings still involved in trades. Okay, so when do I sell? When do I buy? And because the work, so there the work is interesting because It relies on a lot of information that we're going to gather from the environment, from wearable sensors that you may be wearing. A lot of the information that we're gathering is unreliable because by the time we gather it, it may or may not apply, okay, because of the connectivity problems. And then there are a lot of security and privacy issues concerned. We want to make sure that the information is under your control, not under someone else's control. And this is something that's already happening in a different context. So if you have an iPhone and you upgrade it to iOS 9, Apple claims that it's better than Google because when it gives you predictions on, it's time to go to the airport, the information never leaves your devices, as opposed to Google, that mines your email and everything on their own servers. Okay, so there are issues like that are also involved in this.
Not to forget the native detail of my question, but so I'm wondering about, so you have to have these models for where these biases are coming from, right? And you've presented mostly the kind of bias that comes from one person being presented information in a certain sequence, right? So, and they have some kind of a memory, whether conscious or unconscious, right? And some of this information that's preconditions, whatever you decide. But the scenario that he presented in the horizons, right, the explosion, had another component. There were a bunch of people in the room, right, and somebody mentioned somebody hypothesis, whatnot, right, and there's all kinds of other sorts of biases which come from the other people who are in the room. Maybe I'm thinking, yeah, he went to a better school than a whatever, right? He's probably right or something, right? I'm wondering if these kinds of biases, which are kind of, seem to me like sequential or depth kind of crossing versus a wide kind of information that you get, I'm wondering whether they show up differently in your model. And I have no idea.
Okay, so I'm going to take the question and break it into two parts. Okay. So there is one part that has to do with the fact that I am getting information from sensors, but I'm also getting information from different human beings, okay? So the part about getting the information from different human beings and my own familiarity was the problem, because the less familiar, the more prone I'm going to be to certain biases. Take your word, or you come from better school, you're more senior, better, whatever. These things can be taken into consideration in these types of models, okay? And there is other work that's not ours in which people, for example, have looked at the estimates that analysts come up with. And so they look at, there is data that you get, but I'm also getting the estimates that some other analysts have come up with. And I use these to update my estimates. And the way I'm going to weight these different estimates will have to do about how I feel relative to these, or how I feel about their access to certain information. So that part can be modeled within these models. What these models do not incorporate is that there is another effect, which is the social interactions that happen. You believe something, I believe something, then we exchange information. There will be other updates that happen. There are biases that are more community or team or company. So you're new to UBC after a few years, if you've been here like Rabab. After a while, the culture will seep into you, and you'll all look at some problems from the same lens, using the same lens, as opposed to somebody coming from outside who might suddenly see, why is this, okay? And you're not questioning that. So these other biases, I'm not aware of work that has solved these more network group problems, or where there are dynamic interactions. At this level, I'm just getting the information and I make a decision and that's it. But that decision is not the final decision, because I'm going to express that decision, or I'm going to take some action, somebody will respond, and so things are going to change. So that part isn't touched yet.
metacognition, because we need to know how much we know in order to trust the system. If we know, if the confidence level of our knowledge is low, then we trust the suggestion of the system, and if we are confident about our knowledge, then we may ignore the suggestion.
So, so I'm sure that in the psychology literature they have studied these types of problems. In fact, my daughter is studying another interesting problem, and she's more in psychology, and it's not an electrical engineer, in which she calls it the imposter syndrome. And essentially, it's sort of the opposite of what you're saying is, you know, you're promoted, you get to reach a certain level, you become a leader, and you feel that you're an imposter because you think that you don't have what it takes to have reached that level. Okay, so there is work, you know, presumably happening in this area. Within this context, the way that we do it is that the hypothesis is that if I put you in certain situations that mimic the situation you're going to be in, then I can learn, in some sense, your confidence in certain things. And that's what I'm going to use and perhaps adapt in real time. Okay, so I'm not trying to explain, I don't ask you questions, but I'm going to put you in situations in which you are going to make certain decisions, you're going to behave in a particular way, and from that I'm going to learn my models. Okay.
Okay, so if there are no further questions, let's thank the speaker again.
Okay, thank you.